Hello everybody, this is lecture 4 of Signal and System course. Today we will speak about the energy and power signal. First, in any electrical system, the instantaneous power that you take it over any resistor or any electrical element that you have calculate before the resistor of this element or this system. So you have the voltage that's coming or this is between the 2 points of this resistor and the value of the resistor. So the power, as we know before, this is equal to voltage squared to over the resistor, or it is the resistor multiplied by the current, the square root of current, the square of the square of the power. So the current that's coming across this resistor. So this is the concept of the instantaneous power coming from the electrical any electrical system. So therefore it is using this concept we usually calculate the energy and the power of the signal as it's the square value of the signal itself. So so make sure and concentrate now. So now the energy of the system is different from the power. The energy is the square of the voltage here, the square of the signal, the x of t squared, and we usually take the limits to the infinity from minus t over 2 t to t over 2. So this is for the any signal, and for any signal it's if you take from infinity to infinity to apply the limits, then you will take the energy as this, and this is for the continuous time. So you may be memorizing this equation, because this is important to calculate the energy, not the power, of the continuous time. Okay. Now for the discrete time, it's different, because here we take the integral of the square root of the signal. However, sorry, it's for the square of the signal, not the square root. Sorry. For the discrete time, you just make a summation. You calculate every element of the signal over the from mine over the n, from minus infinity to infinity, for the also for the square version of the signal itself. Okay, so let's see how it's if we have a signal like this from 0 and coming up to a and returning back to 0 and returning back to b and then returning back to 0. So this signal have some voltage, have some power on it. So to calculate the energy, we take the square of this signal. So everything is squared. If it is minus, it will be in positive. So this is the square of the signal, and then we will take the area under this signal. That's why we take the integral, or we in time in discrete time we calculate summation, sum all of the signal points over the n, or over, or the calculating the area under this, the gray area that you see it under the signal energy. Okay, so an example we take here, he give you an example. Find the signal energy of this signal, and he gives you this signal x of t equal to two rectangular signal, and it's shifted t a scale t over 2 minus 4 rectangular t plus 1 over 4, and all of them multiplied by unit function of t plus 2. Okay, so as we know, first we write the equation that we use. The equation is from minus infinity to infinity of the square of the signal. We take the integral over t, or over the time. Now So we will just copy all the signal or the functions, and we take it over, take the square of it, and put it under our signal. Now, first, we have, this is main function that multiplied by both of them. The main function is u of t. As you remember, u of t is from uh, from 0 to 1, and it have a value of 1, and it's 1 to the infinity. So here we take t plus 2. T plus 2 means that the signal is shifted. The plus t, the new t is equal to the old t plus 2, so the old t, it will be t minus. So it is in shifted in minus, okay, by 2. So just 1 to the infinity and shift it in minus. And before it is 0. It is 0 before. So here, the multiplication of anything multiplied by 0, it is 0. So it is the signal that we have, it will be 0 0 0 0 until minus 2, and then it will be 1. So the 1 is multiplied by anything, it will give you the same exactly this thing that you have. So we will remove ut plus 2, and we will put limit our integral from minus 2, not from minus infinity, to infinity. And we multiplied here by 1. 1 to the power 2, it is 1. So we have now this signal. Now return back to the mathematics. We have a brackets of two function to the power 2. So square of the first one, 2 to the power squared 4, square of the rectangular function, square of the second one, minus 4 so it will be 16, and this is will be squared. See here, squared. And then the first one multiplied by the second one multiplied by 2. So 2 multiplied by 4 by 2, it will be 16 minus 16, the same sign. And then this one multiplied by this one, the rectangular of t over 2 multiplied by rectangular of t plus 1 over 4. So this is the simplification, or the expanding of this function, so we can take the integral easily now. Now let's have a hint about rectangular, because I think I didn't give it to you before. So the rectangular function is like this. It is defined as 1 here, 1 for t less than 1 over 2, and 1 over 2 for t is at the value of 1 over 2, and 0 if the t is higher than the absolute value of higher than 1 over 2. So what is that meaning? That's meaning that it's before 1 over 2 minus 1 over 2, or positive 1 over 2, because it's here it is a absolute value, it is 0. And for this value it is 0.1 over 2, this one, that's why this one, see, this is the actual one, and this is the one that the representation that we use usually. And 1 if it is less than 1 over 2, from this point to this point it is 1. So that's the function that we work with. It is a rectangular function, have a amplitude of 1. It is beginning from minus 1 over 2 to 1 over 2. Okay, so now let's apply the here I want this one, and I want this one, and I want this one. This one I already take it from here, so I want, and this one I already take it from here. So I want the function. What is the meaning of function rectangular t over 2? How I can take the integral if I don't know what is the function that I have? So, and I want this function also. Now let's focus on this function, a rectangular t over 2. If you remember from last lecture, t over 2 meaning that this is a scaling operation, a scaling operation here, a scaling operation in this function, and it is t over 2, not 2t. 2t meaning that's compression. So t over 2, it is meaning that it's expanding over t. So the new t over 2 equal t. So the new t, it will be multiplied by 2. So every point here, it will be multiplied by 2. So this point, it will be multiplied by 2 and move to the new one. So 1 over 2 minus 1 over 2 multiplied by 2, so it is 1. So whatever is here, it will be at 1 here. So and whatever is here, it will be at 1. So the result, it will be an expanding of this function from minus 1 to 1. Okay, so that's the first one. It's very easy. The second one, the rectangle of t plus here, where is it? Yeah, t plus 1 over 4. So I will take this, it's a multiple operation. Multiple operation meaning that there is a shifting here to the minus, and there is a compression here, an expansion, sorry, an expansion by 4. So it will be from 2 to 2. Yes, so sorry, so here it will be shifted to by 1. So it will not begin from 1 over 2, it will begin from minus 1 over 2, because you will sum minus 1. So minus 1 from 1 over 2, it will be 1 over 2. So it will be shifted like this. And minus 1 from 1 over 2, it will be at 3 over 2. Okay, minus 3 over 2. This is the shifting. And expansion after that of this shifting, the expansion, it will be expansion by 2. So you will remove the 2, 3 over 2 multiplied by 4. So it will be at 3 multiplied by 2. So it will be at 6. And here it will be at 1 over 2, minus 1 over 2 multiplied by 4. So it will be at minus 2. So from minus 6 to minus 2. Okay, this is the resulting. Now here, as we see here, I will apply the integral. Now as I understand what is our function here, I will apply the integral to each one of them. So I will just, this is a simplification of the integral. It will take the integral of the first one, the integral of the second one. Yes, this is just a constant number, so it will be outside the integral. Now this is the application of this signal. Now why I do understanding what is this signal, so I can do a function applying the what is I understand now from the integral. Yeah, so what is the I used from here? From here the function is rectangular over 1. So the square of the signal, it's 2. So the square of the amplitude, and so if you multiply two function by each other, rectangular and rectangular, at the same period, so as 1 by 1, it is 1. It's a second, it is the same, because you multiply this the same signal by itself, and here the same already. Okay, so you don't see the square here, and here you don't see the square. Now you will see here that I removed, I put the same scale or the same limits of the integral. I didn't do anything here. I just removed the power of the signal, because you just multiply the same signal by itself. That you will take, you multiply, and this is 1. So that's why you didn't see any effect on the power from outside and the amplitude from the outside. Now I go to the next step. The next step, you will just remove this one as it's 1. Yeah, here it's from 1 to minus 1 to 1, and the amplitude is 1. So I will before it is 0 and after it is 0. Yes, so from minus 1 to 1 it is 1. So from minus 1 to 1 it is 1, and everything is 0. So just remove it. Now here it is from minus 2 to 1, it is 1, and before and after it is 0. Here as you see, it is a multiplication of a higher one by a lower one. This is because of the 4, it is higher in the space that's covered. However, this is smaller. This is from -1 to 1, and this is from -2 to 1. So usually if you multiply anything by 0, then it will give you the smaller one. So if you have two function and one is covering a small place in the time scale and one is covering a higher scale, usually you go to the small scale because it is otherwise it is 0. Okay, now we have 4 multiplied by 1, just 1. So here the integral, it will be over t. So the integral of 1, it will be t, and have the limits from -1 to 1. The t from -1 to 1, one time it is be 1, one time it will be 1 minus 1. So 1 minus minus 1, it will be 2. So 2 multiplied by 4. So every all of this one, it will be 2. 2 multiplied by -16, 32, and this is 8. This is it. Just you will remove the limits, so it will be 1 minus minus 2. So it will be 3. 3 multiplied by 16. So just a simple solution of some integrals, some small simple integrals. Then you will have the energy of the signal. Okay, now here the energy and the time average. If you I want now the to calculate the power of the signal, not that energy. The power of the signal is the average or the time average of the energy. So the square of the signal, you will take it from the same value, but you will take the average from outside here. Yes, and for the periodic, you will take the limit, remove the limits. Okay, so you just take the signal like this. So 1 over t from minus t to over 2. So t here is the fundamental period now, and here is the fundamental period, or fundamental yes, it's fundamental period also. Now, so this is for the discrete time. We will take it as a limit. So we have, because it's not limited to places, not just from minus infinity to infinity. It's not continuous. It is a non-periodic signal, or this is the general equation, and this is for the periodic signal actually. So if this is the difference between the signal here there and the energy, we just take the summation in from minus n to n, and the average power we divide by n, or we divide by t. So this is an average of the energy of the signal. Okay, so let's take an example. So if I have an average, or find the average power of this x of t with the fundamental period was 12, and the one of which is described by ramp. If you know ramp, it is 1 t. It is the signal of t, and to the power it go up. Okay, so this is, you will take it from -4 to 8, not from infinity to infinity or something. So now here you have some work over t. It is inverse, so it is not coming from this point to this point. No, so it's inverted in time, inverted, and then it is expanded. It's not t normally, it's expanded over 5. Okay, so now if I put the function, the equation 1 over t, some the integral of x of t to the power 2 d of t. Now I will just put my equation ramp minus t over 5 to the power 2, and from -4 to 8 the integral limits, and it is over, from outside it is over 12. This is the period. Okay, now what I have here, that my signal, it is from -4 to 8. So it is from minus 4 to 8 is ramp t. So everything before it is zeros until it's zero, if you remember. But because it is reverse it, minus t here, so it is the opposite side. Okay, so it will be from minus 4 to 0, because from t to 8 it is 0 already, so we don't have any signal or representation of the signal. Or the representation is 0, so the integral of 0 is nothing. So from minus 4 to 0, it will give you minus t over 5 to the square. So it is just like this, because ramp is actually t, in, if you remember from previous lecture, it is t. So whatever inside the ramp, this is will be the function. So it is will be minus t over 5 to the square 2, and the period it will be limited to minus 4 to 0. Now I will just calculate what's happening here. It is very easy. You will take the power to this t, so t to the power 2, the minus is removed because it's minus minus is positive, and 5 it is 25. 25 it will be taken outside, so 1 over 300, and t, the integral of t square, you will plus 1 over the new power, so t to the power 3 over 3, and the limit is from minus 4 to 0. So one time you take it as 0, one time you take it as minus 4 to the power 3 over 3. So this is the value, minus minus this value, you will get this final value. Okay, now another thing or information that you want to know, it is that if a signal, I have a signal and I calculated the signal energy, and the signal energy gives me a finite number at 12, 15, 0 0.4, 0 0.5, then this signal we call it energy signal, because this signal here, it is a infinite number, it's not zero. The signal have a value of the signal energy, and it is not infinity, so its energy, it's not very very high to it's going to infinity. Okay, that's why this is a signal that we call it energy signal. If the signal it have an infinite signal energy, then it will be and have an finite average signal energy, signal power, then we call it a power signal. Then if you calculate the energy for the signal and you find that it is zero or infinity, if you find it's infinity, and if you take the average of this if you calculate the powers of the signal, and you find this that's power, it is from 0 to infinity, it is limited from it is have a number, a value like this one. This is 0.0711, so it is have a value average power. Then this signal we call it power signal. Okay, so this is just an explanation or a definition. Okay, now we have an example from the book. This example is 1.6. He said that for this two function, two signal, what is the total energy of the rectangular pulse in figure 114b, this one. So we apply the limits here, we apply the function, this function. Okay, what's what we have here? What we have here is from an x square of t. What is t here? T is a square root. A square root, as we said before, you will give the amplitude of the signal, and you will get the limits. You will put the limits. Yes, so the amplitude is a square. Yes, so this is a squared multiplied by something, no, nothing, and from minus t to the over t2 to t over 2, t1, here t1 over 2 and t1 over 2, because it's like symmetrical around 0. Okay, so the a square will be outside, and see now it is from minus t over 1, t1 over 2 to t1 over 2 of 1 here, so it will be t. So this t, it will be 2 of t capital T 1 over 2 minus minus t1 over 2, so it is positive, so the half of something and plus the half of something too, so it will be t1 multiplied by a square. Okay, so this is just a value, so it's the limits to the to infinity, it will be the same. So this is the output, a square multiplied by t1. Now what is the average power of the signal here? This signal, this is as we see here, it is periodic signal. So the periodic signal here we have now, that's a it x to x to, we all every time we write this equation and we try to find what is the signal that we will apply the equation to, and we find the power. So what is x of x2 or x square of t here? X square of t here, it is as a value of 1 here, to minus 1 1. So what is t here? T here, it is 0.2. Okay, so t is from outside here, and it is a square, so you will take a square. A square is 1, because a is 1 here. So a square 1 1 to the power 1, so it is 1. So I take 1 here, and t over 2 and t over minus 2 over 2, so it will be giving me t over t, it will be the whole power, it is 1. That's why this is, we call it a power signal. Okay, that's the end of this lecture. I will try to upload some more examples, so you can practice on these examples. And also there is some problems in the book. It will be like an assignment, so you can practice it calculating. Usually I refer to the some basic integral, and end of the book there is an appendix which gives you some integrals that you can refer to from calculus or from algebra courses. Okay, thank you very much for listening. Goodbye.